Yeah, so good afternoon, everyone. My name is Prathamesh, and today we will be presenting this term paper idea, which is attacks on the last level cache via sampled cache, right? So we all know about the traditional cache attacks, which are carried out like covert channel and side channel, which are basically carried out on the actual cache sets, right? But we are trying to deploy some attacks, but there are some countermeasures developed, like the hardware performance counter. So you just can't develop a trace which is completely thrashing, right? So that's the limitation there. But the sampled cache is relatively untapped area, and there are some micro architectural advantages which we are somehow able to exploit it and deploy some attacks. So we are looking forward for such kind of attacks. So
Can you explain what the sample cache?
yeah, I will explain. Yeah. So, guys, my voice is audible, right? Clear?
Yes, Prathamesh.
Yeah. Okay. Thank you. Yeah. So, this will be the model which we will be looking at. So there will be, let's assume for now that an attacker is running on one core and victim is running on one core, and the last level cache is the shared cache, right? So I would like to touch upon this point, which is specifically the translation of virtual address to a physical address. Now, what exactly happens is, let's say there is a 48-bit virtual address and the page offset is 12, right? So 4 KB page size. So 12 bits are there. Now, during the translation phase, what will happen is it will be get converted into 32-bit physical address. Now, the beauty here is the page offset bits are not changing, right? And when we map the same 32-bit address to the last level cache, as our last level cache is a physically addressed cache, we see that the 12 bits which are not changing, out of that, nearly 6 index bits are visible. So for students, those who are so so we can see that this 600 bits are visible. So attacker can actually exploit these things to deploy an attack, because the very purpose of creating this virtual memory, virtual address to physical address, was to ensure security. So at an operating system level, it is being satisfied, but because of these recent attacks, people are trying to exploit this feature. Now now what happens is the attacker will not be able to successfully deploy an attack because not all the set bits are is in control. So we'll not be able to access.
The page offset is in the control of the attacker, and that's what he's going to play with.
That's what he's going to play with. Yeah. So, and all the traditional attacks also use this kind of technique. So any covert channel or side channel which we are studying as of now, they are also exploiting this, because if they are not having this feature, then they can't, particularly create an eviction set. So, yeah. But what happens is, in the modern operating system, the 4 KB page size is no longer sufficient to, give the demand as per, because the accesses are scattered. So there are a lot of page faults. So the modern operating system, what they can do, they can dynamically do that. But even workstations or server machines, 1 MB, that is 20 bits, 1 MB page size is often common. So if it's not common, then the attacker has developed a code which is known as a pointer chasing code, which specifically creates this kind of page faults, and it tricks the operating system to kind of create a big pages by merging the pages.
Okay, so that is only for one application or for all the applications?
For all the applications, it will collectively look at the access patterns.
Okay, so if let's say the attacker's program is very flashy,
Right.
and that's why he decided to go with larger pages. So, but what is the need to change for the other programs? Is it some constraint of the way page table works?
Yeah, I think so. I think so.
Okay, so what just thought of front, right? We have the no stop reaching anyways.
Right.
Isn't it? Now, if we can still stick to the 4 KB page, right? And prefetch the next page or the two next pages and all, that will be also okay, right? Because efficiently we are still moving 8 KB or 12 KB of data between the secondary memory and primary memory,
Right.
but nothing major changes in the page table.
Yeah. Yeah, I think prefetching from SSD to DRAM, right?
Yes.
Yeah.
OS is the
OS is the one. Yeah. Yeah, I think so. If that approach should be workable, but I think this research in the clubbing, that is the super pages, what they call, by clubbing all the pages, this is actually
they are clubbing the consecutive pages. It's not that they are picking 4 KB from one
Yeah.
location, 4 KB from another location.
Yeah.
A simple next line prefetcher would work wonders.
Yeah. Perhaps I have not looked
Next
at
page,
that
yeah.
next page prefetcher. Yeah. Yeah. But are there any concept of prefetcher at that level?
We can introduce.
Yeah.
Because see, the part I'm more curious is why is this decision taking being taken at the system level? Why the other application should also use larger pages?
Right. Hmm. Yeah, actually, it's a point two. Yeah, point of one.
Continue.
Yeah.
This is nothing related to the attack as such.
Yeah. Yeah. Sure. So, so this thing is there, in which if the page size is 1 MB, then the 20 bits of page offsets are unchanged, even with the translation. So if we look at it in the cache mapping, we see that now all the set index bits are visible. So attacker can pinpointedly go to a set and create an eviction set there, right? So this makes attacker's life much more easier. So now all the
Here, one other assumption is the attacker knows the size of the index. Is that the case?
yeah.
Okay. Any prior profiling thing that is there, or how do we know the size of the cache?
I think they
Here, not
have
the size, right? Primarily the index.
the index bits, yeah. I think they do the profiling beforehand.
Ah,
Beforehand, they do the profiling, and that's why all these attacks they can work on one system and it cannot work on other system because the eviction set itself will get disturbed. So if let's say the cache size from 4 MB to 8 MB it went, right, and the number of sets increase, or in a multi-banked way, the banked bits will also be there. So that also they have to exploit. So they have to do some kind of profiling. Yeah. So now coming back, so by keeping this thing in mind, we'll address this thing shortly. So now we will go to, a sampled cache concept, right? So the concept of sampled cache was, introduced for the state-of-the-art cache replacement policies, which try to mimic the Belides optimal. So there have been replacement policies ne- late, lately, which is known as the Hawkeye and Mockingjay. So let's assume that this is the actual last level cache, which is having 2048 sets and 16-way set associative. So what they have to do is, we have heard about this concept of sampling, right? To sample few sets from the cache and maintain large history of previous accesses for that sets. Now the assumption behind this is that the cache access patterns are kind of uniform, which is a very old assumption which carries from the last replacement policies like DRIP, Sheep to Hawkeye, and Mockingjay. So this assumption, what they do is they try to sample few sets, let's say 32 or 64 in this case, and then they try to maintain a huge past accesses to that cache accesses. So their assumption, like in the Hawkeye and Mockingjay paper, is they try to look at this past accesses and they have developed an algorithm which is known as OPT-gen, which tries to recreate the future access patterns like a melody. So look, they are standing at the present, they are looking at the past accesses, and they are predicting future. So their basic presumption was that the past events are good reflector of future. If that presumption fails, then their ideas fail, right? So they kind of devise a fallback option, but that is outside the scope of today's talk because this is the thing. So logically, it should be like a 128 way, and this is uh, simply a structure which is maintaining only the tag bits and all the timestamps and all the metadata thing. It's not that the actual data is there, right? So, so this is the way. But the delimitation of this, now this is not mentioned in any paper. This is just out of pure insights that they are not deploying this in this manner because there are 128 accesses, right? So let's say the cache is 16 way, so 8 times the accesses they have to store. So it's 128 accesses per set, right? So if we have to go and check this 128 accesses at any point of time, there has to be a parallel lookup for 128 tag accesses, which I think is impractically from design constraints. So looking at this, both the papers, what the authors do is they try to, make it, in a distributed manner. So they increase the number of sets and they reduce the number of ways, right? So by doing this, what happens is initially, which was a 32 set 128 accesses, is being shifted to a 5 and 2 set with 5 ways. Yeah. So yeah. See, see. So basically, what is happening is this is there, right? So basically what is happening is these 32 sets are there, and corresponding to this particular set, there are these 128 previous accesses which are stored. So 128 previous accesses which have been accessing this set, the entries are stored here, right? Now what happens is whenever there is an access to this set, let's say there is an access to this set, then what will happen is the approach is they will go and look back here, and they will see at what timestamp it was accessing the cache, right? Now based on the timestamp, they will take certain decisions whether to give RRP value of 0, 1, or 2, right? So to distribute the RRPV values. So this previous history they need, right? Now the fault line here is that for every cache access to a sample set, they need to go and check for this all 128 entries, right? So it's virtually like a 128 tag lookup. So this has its own limitation because there has to be a parallel lookup at all the tag entries, right? So I think this is a pure insight. It's not mentioned anywhere. This is the insight which we have picked up. And for this reason itself, the authors, even in their implementation in both the papers, what they do is they shift this structure to a structure like this, in which the number of entries remains the same, but it is just like a 512 set and 5 ways cache. Sorry. No. So yeah. So basically, the point is for previous 128 access, what they mention is some access are repetitive, and they just have to store the timestamp. So they just merge it there and update the timestamp. So it's like 80. So 32 sets and 80 ways, and 512 sets and 5 ways. Yeah. Yeah. So basically, it's giving them advantage that they don't have to don't have to store the repetitive entry, because they just go there and update the timestamp. So because they just have to. Yeah, so past 80 accesses, yeah. 80 unique ones, right? But that too must be having that overhead, right? For searching the tag bits and all. Might be some energy constraint. We don't know. This is purely insight based. Because that's the reason. So even the authors mentioned that they are using this, but when we look into the implementation design, they have used in this manner. And in the Mockingjay paper, the authors have specifically mentioned that they have shifted from this design to the new one. So that's the author's thing, and we are taking this, right? So if this is there, then there are 5 and 2 sets, right? So we have to index this 5 and 2 sets, but this indexing to this 5 and 2 set will only come from the sampled cache, which in our example is only 32, right? So with this, what the paper is doing is both the papers, they are using 5 bits for set, and they are using 4 bits of the tag, right? So a combination of these two will give them the indexing for this sampled cache, right? Now when this indexing is happening, we will go back to our present slides in which we have seen the translation thing, right? Now in this we can see during the translation, not only the index bits are visible, if the page size, if the page size is 1 MB, 4 bits of tags are also visible, right? And now till date, no one has tried to create an attack using tag bits, because tag is generally not used for indexing. Only the set bits are used. So although it was always there, nobody has ever noticed that these tag bits can be there. And now what we can do is we can exploit these tag bits, because the same tag bits are used to index this sample cache, right? So when the same tag bits are used to index the sample cache, what will happen is an attacker, if he has a control over these tag bits, can direct his accesses to one of those 5 and 2 sets, right? And he can do it with good accuracy, because he just have to find 32 sets, because the lower order 4 bits are in control. Now what will happen is the accesses of the attacker will 100% go into one of these 32 sets, which is 5A, right? Now what happens is we will go into detail, like what happens if there is no attacker, if there is a normal execution of the program, right? So the attacker has access to sample sets, it will definitely go into one of the 32 sets. Now let's look at a situation in which a normal applications are running, right? So what will happen is there is an access to cache, the entry will be put into the sample cache, right? So the entries will be put here, right? So what will happen is when there is again an access to that entry, it will check into the sample cache. When it will check in the sample cache, if it is a hit, then what will do, it will calculate the reuse distance based on the timestamp which has stored. And then what it will do, whichever program counter has brought this particular block, they will go to that corresponding counter and increment that value, because it says that it is found in sample cache. This means it was there, it is calculated. The algorithm says that there are highly likely chances that it can get hits in future accesses. So that's their play. Now what happens is, this is the normal case. Now let's say we are an attacker. So what an attacker can do, victim will access its block in its own fashion. The attacker can go and just trash the sample cache part of it, right? And there are two things here. One is, we know sampled caches beforehand. That's the assumption. And second assumption is, we don't know what are the sampled caches. So the first one is easier to deploy because we can specifically go to that particular set. But the second one is really the long shot, in which we can use this information to regain or to predict which are the sample sets. Now that's the long shot. So what will happen is, when attacker will access this particular cache set, it can surely do it with good probability. So what will happen? There is a LRU replacement policy which is applied in the sampled cache, right? So when the LRU replacement policy is there and the sampled cache set is full, it will evict one of the block. So here now V1 will be evicted. Now what will happen? When the V1 is evicted, it will place its own block there, the tag bits. Now what will happen? As something is evicted from the sampled cache, the logic itself says that, okay, we have given it enough time. There is not any access to this particular block. This means that we might be going in the wrong direction. So what it does is, it evicts it, and corresponding to that program counter which brought this block, they decrement the counter, or increment means they are giving it bad value, lower value, right?
And when you say this particular V1
Right.
being evicted from the sampled cache,
Right.
the actual cache is still there.
Yeah, it may be there, it might be there, it might not. It's completely a different structure, because this is just previous access to the actual cache, right? It's like previous accesses to the actual cache. It might be that there might not be, all the elements will not be there in the actual cache. It is completely distinct structure. So it is just used for prediction. Actual cache things are going as they are, right? So what will happen is, it will decrement. So in this way, what will happen now, if the actual block, right? Now if the victim is again accessing, it will see, and it will come, and it will see that it's a miss, right? As opposed to hit, which was in the earlier case, right? And now the predictor will be again getting trained negatively. Whenever there is a miss, it sees that, okay, it's not a good block.
But for some other PC.
Yeah, but this block V1 is brought by the same PC, right? Another PC can also block it. Yeah, so that's the point. If it does for some other PC, then it's more dangerous, because there are follower sets, right? This is only happening in the sample sets. If it does for some other PC, then even the blocks which are in the follower sets, they are getting affected with their RRPV value, because we will come to that point. Yeah. So this is the crux here, right? So what happens? Let's say this is the thing, and yeah.
So it is going to change the future of that.
No.
Prediction of that.
Yeah, future prediction of that block. Yeah, it's going to change the future prediction of the block, and the future prediction we do is just by pasting the RRPV values. So any block which is incoming, we just have to decide what RRPV value we should give it, right? So it's based on the PC based predictor, which is a standard predictor used. So let's say an access is to a non-sampled block here, right? Which is not from a sampled cache, right? So what will happen is, it will go and check into the predictor. It will see what is the counter corresponding to that program counter. It will look at the history, and when it will see the non-compulsory access, the reuse distance, and the expected time of return for Mockingjay paper, and RRPV value for Hawkeye. So both are symbolically similar, only just differences in name, right? So new value is put there, right? So based on this, because the program counter says that its counter is 100, that means it was given enough chance, but it didn't perform well, right? So let's put it with a higher RRP value, so that in future it will be evicted faster. So that's the prediction which they are playing on, and this is what we are tapping. That if we can get this prediction hampered, then we can forcefully put some blocks which are actually cache averse, but we are pretending to be cache friendly. So in this way, the attack works. Now let's say, attacker has successfully increased the eviction priority of victim. We can see here, the attacker has successfully increased the eviction priority of victim, as greater value means near to eviction, right? Now let's say, what are the key insights, right? So the first insight is the basic one: we can mount a performance degradation attack. in which one thing is very sure. I will come back here again, which is that because of this four tag bits continuously in your control, this is not only the 000 bit. If in like side channel attacks or covert channel attacks, in which the attacker just skips the higher order, the upper levels of cache, right? It skips L1, L2, all the accesses, the code is written in such a way that most of the accesses go to L3, right? Which is not the case in victim. So victim has to go through. So the number of accesses to LLC of attacker would be more as compared to victim, right? So in this way, what he can do is when there is, let's say, one or two accesses of victim, an attacker can, access a lot of entries in the sample cache. So just by flipping this 000 to 001, what you can do, all the 32 entries just below that entry can be swapped away. So if we are having that control, entire sample cache can be flushed out. So if the entire sample cache can be flushed out, there will be a serious performance degradation attack, and all the entries of the victim will be giving higher RRP values and be evicted very fastly. So it's just like degrading the performance completely. So this is the first approach, the performance degradation based attack. Now we can also go through the covert channel attacks to the sample cache, right? So how can we do the covert channel attack is in which in this there will be no attacker victim, there will be a sender and a receiver, in which the sender and receiver can purposefully predetermine that if you are accessing a particular of the 32 sets of a particular, and this is very precise also, because in normal case it will be scattered, right? But in this case, now sender and receiver both have control of the tag bits. So what they will do, they will randomly go to any one of the 32 sets by setting a bit, right? And their probability is also high. And then they will check the attacker will put some entry, it will be termed as binary 1, and if the attacker is not putting an entry, the problem is synchronization, as with all the covert channel attacks, and the receiver can infer 1, but there is little bit of more noise with considered to sample cache, because here we can't pinpointedly go here if we don't know the sample sets. If the sample sets are there, then it's a very crystal clear attack. But if the sample sets are not there, then there will be a noise. Because let's say we are setting the bit to be 001, we don't know which of the 32 sets you have to look. So receiver also don't know his actual access will go to which of the 32 sets. So there is a lot of entropy in this. So it's very difficult to predict. But if the sample sets are there, yeah. No, it will be like a standard covert channel attack, in which if the entry in the sample cache is present, then if the attacker will purposefully put his entry in the sample cache and he will preserve it because he is having the control of this, right? And after some time, the victim, the send receiver will come and it will check the entry in the sample cache.
So it is same as the performance degradation will lead to covert channel.
Yeah, you can say not directly, but here you have to make the proper synchronization. In victim's case, what was happening is his accesses were delayed, right? He was not writing his code in such a way that he was skipping all the upper levels cache and accessing it, right? So the same logic of performance degradation can be extended to the covert channel attacks. Just yeah.
These number of checks probably will be complex.
Yeah, no, yeah, that point is there. But see, what happens is we are discussing of the long shot. The best case is the victim has already both knows what are the sample sets, right? If these five bits are known, then it's crystal clear. It can go to any one of the 512 sets. But we are talking about the case in which this is not known, and this is a very powerful thing because if this is known, then everything can be collapsed. But if this is not known, still with some good accuracy, we can create this kind of attacks. And this is the main proposal of our work.
So noise will be more in this case.
Noise will be more in this case. Yeah. Yeah. So basically our long-term target is to I will just explain you. So our I will come to side channel once. So our long-term target is, can we somehow expose the sample sets, right? So how we can do that? So let's say here, right? So let's say here, when we look at this, we see, right? So what the attacker has done? Attacker has purposefully, manipulated this predictor and has put its own value, right? Right? So what will happen is it is affecting victim's value as well as the attacker's value, right? He can do anything. He can decrease victim's value and increase his own values. But the problem here is, the important catch here is, if we can somehow measure the performance impact in non-sample sets, right? So the thing is, whatever we have created, we should be able to quantify it. If we are able to measure it, that means we know that whatever sets we have achieved, they have gone through sample cache, right? Every set we have access has gone through sample cache. The thing is, we just don't know, right? So if and this is really the long shot which we are taking, that if, like in a case of creating an eviction set, right? We just assume that this is an eviction set, right? But creating an eviction set itself is a lengthy algorithm. So if we can follow that eviction set algorithm, which means they take some 32 sets and then they will monitor that for some time, right? And then they will look at that 32 sets and look at the performance. If that performance is getting affected in the 32 set, that means the program counters which are bringing values to this particular set, right? So this set is highly likely, right, that it is being affected, which means one of the sets could be a sample set, right? So that's what we are doing. And the side channel is also a little bit complex, because the code channel can be, as question was asked by Vakar, if we are using flush reload type of thing in which the memory is shared, right? So in that you can flush this sample cache, but not like actual CL flush instruction. We have to do it cleverly there also, right? So we have to go it through the long way. But if case of prime probe type of attack, the code channel itself is very noisy, so the side channel will be much more challenging there. But these two things, the last 2 points are, looking for future directions, but we will primarily be focusing on the performance degradation attacks. So on the side of implementations, we have figured it out how to create traces which can exploit visible sets and tag bits. So this thing we have done of the infrastructure, and for the time being, we are trying to create some synthetic traces in which the 4 bits of the tag are is in control, and try to sync it with the receiver end, so that we can access it whenever we want. For first is performance degradation, and once the performance degradation is established, see, performance degradation is very easy. You can even run another application on multi-core thing, because that will also evict it, right? But the fact is that application should be highly streaming. It should be thrashing all the cache sets, though performance degradation is visible there also. But the point is, as it is not exploiting the upper levels of cache, even though it's thrashing, many of the accesses are filtered from L1, L2. So by particularly, handling that bits, we can even show performance degradation without anything. Just running on multi-core thing will help us. But to get very precise, we have to control the tag bits. Because this thing is that this is very scattered. This thing is usually very scattered. So these are like, there will be 32 chunks, and these 32 chunks will be there for one sample set, right? So for this one sample set, there will be 32 chunks. Now, even if the application is thrashing, yeah. So even if the application is thrashing, sorry, this is not there here, I think. Yeah. So for one sample set, there will be this kind of structure, right? So if the application is thrashing, we don't know whether it will go to this set or this set or this set, because the tag bits will be random there, right? So there, just some degradation will be possible. But here what we are actually, I missed this point. What we are trying to do is, we are trying to break the correlation that 128 past accesses are required to get the validates optimal working properly, right? In this case, we are targeting that assumption, because if this case was not there, when tag bits are not in control, that 128 or 80 accesses are scattered throughout these 32 sets 5 ways, right? But now what we can do, an attacker can forcefully go and evict at any stage. So that means an attacker can completely, what we can say, thrash the history, which means the history itself is wrong. Now, when the wrong history is going to the predictor, obviously it is predicting wrong things. So we are challenging that argument, that the 128 accesses which they are storing, we are actually corrupting that with the help of an attacker application, and as this is a shared structure. Yeah. So that basic assumption we are throttling. And as of now, we are trying to mount it on ChamSim simulator. But if we get the basic things right, then we can go to Sniper or some other simulators to deploy some good attacks. So yeah, thank you. If you have any doubts, we can discuss.
So this synthetic traces that you mentioned. So what are its characteristics? Means what are the patterns that you're looking at?
Yeah, so what we are targeting?
So you're targeting LNC, right?
Yeah, only LLC, right? So first, what we are targeting is we are assuming that we are knowing what are the sample sets directly. So in the code of the replacement policy, they are choosing some 32 sample sets, right? So it's like after every 64 sets, we are choosing one set, right? So that amounts up to 2048 sets. So after every 64 set, one set is simple set. So we are taking that one set. We know its set index bits, right? So when we are creating that synthetic trace, we are setting that set index bit to be that, and the tag bits we are setting it to be for the time being to be 000, right? And this trace with all the accesses, and there will be accesses, similar accesses, and we are repeating it for infinite time. And what we are trying to do is, because in the actual system we are trying to deploy it on multi-core, so the accesses will be interleaved, and we are trying, and as per the assignment which we give to recreate that, we have also shown the ways how we can create an access pattern which will continuously miss L1 and L2, right? By after a very long time. Yeah. So that we are trying. So after that, we will just create a synthetic trace which will run in a while loop, which is just like infinite loop. So with that, we are trying to see. So till now, synchronization part is not done yet. So with that trace, what we are trying to see, whether it is able to evict all the entries in the sampled cache. If that is done, then the rest everything will be there. And for covert channel and all, we have to look at the synchronization aspect, which we have not looked at yet, but that will be looking. Yeah.
And out of curiosity, if some technique like repartitioning is already in place,
Hmm.
how would this structure everything would change?
Yeah, see, if way partitioning is there, then it's very difficult for the Hawkeye and Mockingjay itself to function,
That's
because
what I'm trying to understand.
uh,
So, right, they would be most likely working as two separate histories, right?
yeah, but then the hardware overhead is too huge, because actually when we think of
So
separate
how is this
histories,
partition working with the
no,
replacement
no,
policy?
it's not there. It's still not in the literature, not in the domain. Actually, that's a very critical research problem also to look at how the partitioning thing can work with this.
Just probably.
Yeah, it will screw up. Because the access, see, the basic thing which we were first looking at all the replacement policies was that we thought that the history is just like 128 accesses, right, for this path. But that's not the case. And that's actually helping, and that was developed just purely because of the performance and energy aspects, whichever they have been looking. So this thing is the main culprit here. Because here it's not like 128 previous accesses, and it's a shared structure, so even one core and another core can share it, right? So if there is a partitioning mentioned in the cache, so you also have to partition the sample cache, which is very problematic, because now there are timestamps, right? Now you will not be able to get the relative information. Now when we say relative information, if we separate the stream to access of a sampled cache, right? So we will access one particular entry, right? If the streams are separated, the accesses which are relative, that information is necessary, because I have not talked about the OPTGen algorithm which they use, which is like an overlapping sub problem kind of thing, right? So in that case, they need that relative information. If that relative information is not there, then it is very difficult. So there is some solution in which you can do, some partial communication time kind of thing, which is a probable solution, I think. In which what you can do is now these two separate OPT gen things will be there, and one OPT gen will communicate with other whenever it's necessary. So whenever it feels necessary that okay, now I have cached this, see, because they are doing prediction, right? So ultimately prediction means they are putting RRP value. Now if the cache is partitioned, right, one will say I will put in RRP value 7 without knowing what is the access of other. So the partitioning itself is not working properly here.
Okay. So let's say we have the base case 16 guys, and
Right.
we uh, we are just sharing this particular cache with two applications.
Right.
So we'll start from some point like this. So six ways are dedicated to each of these cores,
Right.
and there are four ways which are being shared.
Which are being shared. Okay, fine.
Right now, these accesses would be pertaining to only those four ways or the entire 16 ways.
No, no, accesses is for the entire 16 ways.
Why is that?
No, no, in the way in which it is stored in sampled cache.
In general, are these guys able to listen to this discussion?
Navneet Keshav, you are able to hear it, right?
Yes, yes, Prathamesh.
Yeah, yeah, okay, yeah.
If I switch on the speaker, it will echo.
Yeah, yeah. So Dr. Kalyan's voice is audible to you, all right?
The volume is kind of low, Prathamesh, but yeah,
Yes.
it's fine. Yeah.
What you can do?
Yeah. No, no, okay.
Yeah, yeah. So, I mean, sit here. What I have to do is there is one. Yeah,
No, no.
but it's only speaker, right? My one. This is also mic. Yes. I'll put it.
This is yours.
Yes.
Some kind of echo is there.
Yeah. Guys, are you able to hear me?
Yes, Kalyan. Now it's clear.
Rohit, can you hear?
Yes, Kalyan.
Should we battery? No, no. Can try it out. Okay. Guys, can you hear us any better now?
Yes, it's much clearer right now, Kalyan. Yeah.
Okay. Yeah. Okay. Yeah. See, my question was with way partitioning, right? And way sharing, you can call it way partitioning, a combination of both, right? I'm saying 6 ways per core dedicated, and there are 4 ways which are being shared.
Right.
So those 4 ways, how do I decide whom to give? Is based on the access pattern of the application. Right. Now, let's say I'm giving 3 ways to application 1 and 1 way to application 2. Means that application 1 has 9 ways, application 2 has 7 ways. Right. Now, this, let's say this particular any set you can take, we are trying to track the accesses. So these 128 accesses, right? You are saying that would be across all both the applications.
All the 16 sets, it will be there.
16 ways.
Yeah, 16 ways.
What is the need? I don't see.
For that, I think for here also we can do partitioning to avoid this thing, removal of these blocks history.
At the sample cache, right?
Yeah,
But the partitioning will again be across the sets only, right? Not across the ways. Or way partitioning, then it's very less, right? It's already not giving them sufficient, the previous accesses because of the long structure. Now, even if you sample that, so that 5 ways becomes 2 or 1, then it's like a direct just storing one history of all the applications, right? If it's mapping there, then it's too easy. So the less the associativity, the performance degradation is that high, or the accuracy of OPTGen to recreate the validity optimal is that low.
Mm-hmm.
So
So you are saying even for partitioning, this structure will not change.
yeah,
That's what.
Yeah.
Uh-huh.
This structure. Even if you have to change, you have to go for some set-based partitioning, some kind of like in the 5 and 2 sets, you have to do it in that way.
Achha.
And one more point I would like to add regarding that partitioning thing.
Mm.
Actually, what is happening is, let's say the 4 ways are shared with both, right?
Now, for that, there has to be a single OPT generator. If there is no single OPT generator, what will happen? The access patterns will get two different OPT generators, right? Now, when that will happen, right? In the three things, you are putting some other RRP value, and in that one cache, you are putting some other RRP value, right? So the replacement for them will be different, right? But when the point comes when you are trying to change the partitioning, right? Now at that time, these two OPT gens should collaborate with each other. Otherwise, they will not know what is happening.
Okay.
And how can you take decision? Because this OPT gen is basically based on number of accesses, right? So let's say there was one access, after there was second access. So that time interval, that usage interval which is saying is based on access only. So then it's again thwarted. Now it's giving accesses. Now you don't know what are the interleaved access. Now when you don't know what are the interleaved access, how can you decide what ways to give and which?
No. See, this OPT thing is only for the replacement part, right?
For prediction part.
Prediction based on which is the possible victim candidate and the best victim candidate, right? With the farthest reference.
No. What basically this OPT gen is doing is it is predicting that this particular block, if it is cached, right, with the help of the predictors, then in future it will get hits. So it is basically setting the RRPV value in the normal sense, right?
Okay.
So if the OPT says that, okay, if optimal was applied, then optimal would have said that yes, it would have got cache hits. So let's put it with RRPV equal to 0.
Okay.
So that's the job of OPT gen. Now for that it requires a lot of history, right? So in case of partitioning, if you're saying that we will go give individual histories, then the first thing is you have to get that many number of OPT gens. If it's just 2 core, then 2 and 4, then OPT gen itself is a huge structure.
Okay.
So that will take, right? And one more hard point on this is that if OPT gen is in silos, it is different two OPT gens. Now what will happen is the access streams which you are feeding to that OPT gen will be particular to that application partition, right? Now when OPT gen will be trained on that, OPT gen 2 will also be trained on that, right? It will give its own. Now when you are trying to change the partition, right? Now which OPT gen you will trust more, because both have seen their local patterns, right?
That is what I'm trying to say. When the decision on changing the partition is not based on OPT, right?
Right.
They are two different things.
Yeah.
So why do we take a call to, let's say, give one extra way to other application? It is based on the overall misses. It's not specifically looking at access pattern or anything.
Yeah, it's looked at number of misses.
Overall misses.
All misses. But then that too is for the sample sets, right?
Right. Partitioning is for all
No,
of
but
them.
they will look at the sample sets only, right? To take the decision, the number of misses.
So there are some works which look at overall. For every epoch they look at the number of overall misses.
But this UCP and all these papers, they look at the sample cache only, the sample sets. These 32 sample sets which are sampled, they will maintain counters corresponding to that for both the applications. So 32 sets, and again that's very challenging because that structure itself again is shared.
Right.
So, but they still go with that. They will count the number of misses for application 1 and 2, and based on that, they will come up with some ratio, and then they will shift the partition. So that's their approach. But still, it's on the sample cache. So whatever happens on the sample cache is ultimately reflected at OPT gen, which translate into prediction. And the key point which we missed here is all the follower sets will also go with the same thing.
Right.
And that's the important part there. So, but the approach which you are saying, that will be different then. If we are looking at counters, eviction counters for the entire cache, then this OPT gen will not come into play.
Yeah. So if just related point is in the yesterday's discussion that we were having, right? If it is a miss in the metadata cache, he's just directly going looking at the counters, and whichever have experienced highest access, he's going to go with that. Okay, go and check this level. Most likely your block will be there. It's a fallback plan. Okay. Okay, so can you go to the next steps part once?
Which one?
Next steps,
Sorry.
the last slide. I
Last
think. Yeah. Huh. Yeah. So implementation thing. So can you share uh, what regarding the work on the first point? How did you figure it out and all?
Yeah, so basically what we have done is to create this kind of cache trace. We as the assignment was given by you for the code channel attacks. So we saw that in the ChamSim implementation also there are some works which have implemented the concept of these big pages in which the page size is greater, right? So even in the access to the last level caches, all the sets are visible. So your actual set index can directly be plugged out from the full address. Whatever is the full address that can be plugged out, right? So that's the point number one. And the new point is in the ChamSim simulator, we have figured it out how to combine it with pin. Actually, I was not knowing that before. So in this what the plan is to write a proper code which will generate all this kind of traces. But that's kind of difficult.
But trace generator is already there, isn't it, for ChamSim?
Sorry.
Trace generator for
the tracer file is already there. Yeah, but we have to write our own trace, right?
Own trace?
Right, means if you are writing a code, right? So to write such a code in which the tag bits are also in that manner, it's challenging. Because we don't know how, right? Because address part we know, because certain load instructions will go on access it, right?
Yeah.
But for tag bits, that's challenging.
Okay. And what about the sampled cache? Is it already some implementation is there?
Yeah. So for the sampled cache, the map implementation is there. We have gone through it, how it is being implemented, and how the LRU policy and all is mentioned. Okay. So it's similar to the tag directory which is there. So ChamSim is based on tag only. The data part is not there, so there is no issue there. And we have looked into the code of Hawkeye and Mockingjay as well. We have seen the inner implementation detail. The sample sets and the indexing part is also very clear. It's the way which is there, they have done it in the same way. So our assumption that these 5 bits and 4 bits are there, it's locking. So they have done it. It's there. Yeah, it's there. It's their code. And in both the replacement policy, it's there. And we have done some experiments also, for the multi-core things. So some performance degradation is there. But as the sampled cache access pattern is scattered, which is actually fitting their assumption. Because they're using these 4 tag bits, they have also cleverly done it, because this 4 tag bits, what it will do now, it will scatter it. Because they know this 4 bits will scatter it around the 32 sets, right? So the 5-way, which is the limitation, no one will be able to, even if one block is entered timestamp time t equal to 0, let's say even after 100 timestamp, there are high chances that it will still be a hit, because the access patterns are scattered.
Okay.
But that's what we are exploiting. By taking control of that 4 bits, we are targeting that bottleneck that only 5 ways are there.
Okay.
So just 5 to 6 accesses can evict the block, and in turn it will lead to performance.
Got it. Now with the Mockingjay implementation, were you able to figure out which sets are being picked as sample sets?
Yeah. In Hawkeye and Mockingjay,
so is it static?
It's static. For now being they're static, but there are some implementations in DRRIP, which is for selecting the sample set. In that they have gone for random sets.
Okay.
But that also will be just for the one program. After it will be changed.
Achha.
So so that's the long shot which we are targeting. That if we can make that sample, or first now on we assume that it is static, but we will not use it to train it, and then we will see that whether based on the outcomes by measuring some performance counters, by looking at that the effect is percolated here. This means among these sets there is a highly chance that one of these is the sample set, right?
Okay.
By doing that, we will try to match up the reverse engineering thing. That is our algorithm by the by putting some thresholds on the counters. Are we able to guess some hint that this set was sampled? Okay. And we are not. So that's
okay.
So as of now, we're trying to create the synthetic trace. That's the primary approach. And there are some hurdles here, but because the trace in ChamSim is just not like address, right? There will be branch prediction whether the branch is taken or not. So we have to look into those minor issues also, how to.
No, but with pin, I think it should be okay.
But then we will not be able to create the same the structure that we want, right? It's doable.
No, no. So I would visualize it as a two-step thing. First, get the complete trace, then post-process it.
Yeah, yeah. First get the complete trace and then yeah.
And okay, that's good. So we were having a discussion last week on TLB's attacks, right? Right. So at that point, there was an open question that if we are scrambling the addresses at the TLB itself, why don't we use that for the caches also? So any thoughts?
Stop the
Navneet?
Uh,
Yes, right.
Kalyan, actually, if we scramble the cache, that will be a big overhead, right? As opposed to the tags. I mean, if we like scramble the whole cache, I mean, that'll give a significantly higher overhead, right?
Scramble the whole cache meaning? I didn't get you.
Kalyan, you were talking about scrambling the cache, right? Like just like the tag array that we used in Caesars.
Right.
Yeah. So I was thinking like if we are scrambling the cache as well, like we used a tag array. If the data array is also scrambled, then that might take significantly more time, right? Because the tag array. I mean the size of the tag array is significantly small as compared to the data array, right? So
Mm, See, whenever a new page is brought in from the
okay,
secondary memory to the primary memory, right?
okay,
Um, at that point, there will be a change in the address,
okay,
right, at the TLB. That's what the randomization thing, right, at the TLB.
okay. I was talking about the remapping stuff as well. I mean, periodic remapping.
Navneet, you can give the context. Um,
Kalyan, I think in the cache, if we unscramble the addresses, then wouldn't that make it more complicated on top of TLB? Because if the cache address is itself not in consonance with TLB, won't
okay. See, the point is, we have an address X, and we are converting it to Y just for the TLB lookup. Okay, but we are using X and looking up to the caches, and at that point we are changing it to Z in the name of randomization. So my point was, why can't we use the Y, which is already being done? Does it make sense?
X is the virtual address, right?
So it can be the virtual address, or it can be the physical address that we get, and on top of that we are scrambling. Either one is fine. Of course, there's some change in implementation we need to do, but yeah.
So in TLB, we didn't exactly scramble the address in the last presentation. We just uh, use different addresses for storing in TLB and to providing it to the CPU for a cache.
Different addresses meaning what?
So the TLB has a request to handle a specific virtual page in the to translate into a physical address, but to translate into a address of page table and to get the physical address. But we are not using that to again store that address physical page table address into the TLB. We are just providing the overall result to the CPU directly by storing it in a buffer and using some other address in the vicinity of the requested address to store the entry in the TLB. So we are just we are asked to do X thing and we are doing Y thing. So I don't think the cache will the performance will degrade greatly in cache because locality is a much bigger factor in cache.
No, but the same scrambled address we can just give it input to cache, right? That is already scrambled. So even if it is in the same set, the no one will be able to exploit the access patterns there. If we can somehow do that.
So let's say we have a virtual address X, okay, and that was getting mapped to the L2 TLB, which is again can be viewed as a set associative cache. Okay, it was getting mapped to set number 100, some way. It's okay, right? Now what we are trying to do is instead of mapping it using X, we are changing it to Y, and that Y will give a new set number. Let's say it is 15, right? And we are storing the physical page no address etc in that in that set anyway. Now the next time there is a request for this address, right, for this page, how do we get Y? We are storing it somewhere, right, Navneet?
Yes, yes, I following you, but
So my point was, if we are storing it, the changed address, why don't we use it?
that was the whole point. We cannot use it because the attacker will exploit it using the reuse pattern of that in the main vulnerability which they identified was the reusing pattern will give the attacker an idea of
But
what
prior to that, one more assumption is the same set at the cache is being used by both the attacker and the victim, right?
yeah, yeah,
Now we are scrambling the set itself, isn't it? So that
yeah.
the possibility of the sharing with the attacker, of course it will be still there because the cache is still shared, but he will not be able to know whether the data which was brought in this time is in the same set or some different set.
Yeah, but there the secure TLB paper made a strong assumption that attacker can itself direct the victim to do accesses on its behalf. So
Sorry, can you repeat
the
that statement?
the attacker can direct the victim to do memory accesses, not specific memory accesses, just memory access as it feels like, and observe the timing of the victim process itself to infer what the victim is doing. If it's taking very less time in memory access operations, it can infer that it is using the same addresses over and over again in the TLB. So that was very strong assumption. I don't think if we consider that attacker has no idea of victim, that then the attack does not make sense because the attacker cannot see what victim is doing. So that assumption was very strong in the secure TLB. And
Navneet, just a small question here. So
yeah,
this assumption which you are saying about this reuse distance, so this reuse distance is specifically for the L2 TLB or for what? What is the reuse distance which attacker is exploiting?
sorry, so attacker is attacker is exploiting the set access. So L2 TLB will be good, but I cannot get what
Yeah,
memory time.
Navneet, so what?
Eviction memory time. I guess I mentioned it that what is the time that victim is taking.
Just correct me if I'm wrong, Navneet. What my point was, it is using some random thing at L2 TLB, right? Because there is a conflict happening at L2 set, it is using some random function to fill that set, right?
Yeah, yeah. So
So when it is using random, how it is able to search for the new address? Then it should be fully associative L2. if it's using L2 random?
I how does it make fully associative? I don't get,
No,
because
no. If
if
if say if let's say if there is set number 10 is accessed, right? Any way of set number 10. Now after random fill, you are saying that we have to go to set number 4, right? So how do we know at which set we have to search? That
no no
mapping should be there, right? How can it be
no
random?
no, the mapping is not random. The the request is done for the set number 10
Uh,
to give a particular page table address. So if there is a miss, it is only in the case of miss. If it's a hit, the attack, uh, it directly gives the page table address. But if it's a miss,
no,
it will
but in
follow.
memory, if it's a miss, it will go to main memory, right? It will fetch from there.
Yeah. I understand, but what it proposes, it that it will not save that entry back to the TLB. It will just store that uh, final page table address in a buffer and then supply it to the CPU for the cache access. It will not store that into TLB. Instead, it will use another address to suppose it will suppose that the request was for some other address to store that entry into TLB. So it is not as if it is mapping the thing. It is not storing that address into TLB itself. It is just bypassing the storage into TLB to serve the CPU directly. So I,
Okay.
Uh, okay, so this paper is anyways due for your summary, right? So I suggest let's all go back, read the paper in detail, and have a discussion tomorrow or worst case Wednesday on the paper.
okay, okay, ma'am.
Any volunteers? So there's some pending work from my end also that I need to introduce the memory level attacks, right? Just 1 second. Hello, guys.
Nice,
Yes,
Khalil.
Kalyan.
Yeah. So tomorrow I'll take the class, right? And if you are able to come in person, that will be good. We can have uh, no good discussions. And these guys will be having tea now, which you are missing. Yeah. Okay. See you guys tomorrow. Thanks.